So welcome. This is a question which is a three-dimensional kinematics problem. So this question says a projectile has an initial velocity of that, plus 5i minus 4j plus 6k. What is its vector displacement after 3 seconds? So let's just visualize it. This is the vi. And next to it, I'm going to write down what it is, which is plus 5i minus 4j plus 6k. And this is meters per second. It's easier to say write it to the side than it is to actually write it to the side. And then it says it's projectile. So let's remember that we also have an acceleration, and the acceleration is a projectile, so it's going to be pointing downwards, and this is going to be 0i minus 10j gj plus 0k meters per second squared. Now hold on, how did I know that? Well, I know that the acceleration due to gravity is 10 meters per second squared, and it points downwards, and downwards is the minus y direction, so it's minus 10j is the vector notation for that. So we'll let this happen, we just let these two affect each other, and what happens is over time I'll get some kind of trajectory that looks like this. And after, well, delta t is equal to 3 seconds. And after 3 seconds, we're kind of here. And it wants to know what the displacement is. So we're specifically looking for this vector here. Again, this is in three-dimensional space. I'm drawing it as two-dimensional, but we're actually in three-dimensional space. So let's call this, well, let's call this R just for the sake of it. This is the vector displacement. So what do I know? I know that VI is equal to 5, V initial is equal to 5i minus 4j plus 6k meters per second. And I figured out that A was equal to 0i minus 10j plus 0k meters per second squared, and I knew that my time interval was 3 seconds, and I want to know what my displacement is, which, if you like, is like a, well, delta x. It's my vector, which is my displacement. So I need to do this, and I need to find an equation that links these four things. And the obvious equation is delta x is equal to vi delta t plus 1/2 a delta t squared. And I want to represent in vector form, so that's vector, and that's vector, and that's vector. So it's the same equation, it's just represented in a vector form. And in order to, didn't mean to do that, sorry. And let's see if we can get this back. And in order to get this to work out, then I need to do my ijk table, ijk. This is just a layout procedure that helps me get the right answer. And the first thing is vi delta t. So basically I've got to take my vector vi and multiply it by the time interval, which is 3 seconds. So rather than plus 5, I have plus 15. And rather than minus 4, I have minus 12, and rather than plus 6, I have plus 18. So that's my first term, all nicely done. And then to this I add my second term, which is a half a t squared, delta t squared. Well, delta t is 3 seconds, so 3 3s are 9, and a half of that is 4.5. And I know that my a is 0 minus 10, 0. So I have 0. I don't have minus 10. I have minus 10 multiplied by 4.5, which is minus 45, and then 0. Now, the operator here is an addition, so I've got to add these two rows together. So I'll get plus 15i. This is minus 12 and minus 45, which is minus 57, minus 57j. This is 18 plus 0, which is plus 18k. And this is going to be a displacement, so that will be in meters. So there's my answer. Let's just find it at the side. It's plus 15 minus 57 plus 18. There's the answer. So again, what I find personally, I find quite stunning about this is that I'm doing a three-dimensional kinematics problem basically in one calculation. So I don't need components. In a way, I'm using components, but I'm representing them very efficiently using ijk unit vectors. And there we have it.